Now we've covered some integrals involving sine and cosine and their various powers, but another pair of functions that satisfy the Pythagorean identity are the secant and tangent functions. And what we want to look at how we can use those and how we can solve those integrals when they're set up this way. They have some rules that are kind of like the sines and cosines, but they're not always exactly the same. So given that same setup where we have secant to a power, tangent to a power, and those integers are non-negative, and this could work for negative integers and it could work for fractional stuff, but we're not going to focus on that now because it gets too hairy too quickly for just straight rules. Now, if you have the case where you actually only have secant functions and it's odd, you have kind of two cases. So, like again, n is 0, so tangent's not there. If it's just secant of x, like if you just have a singular power, hopefully you remember that that's actually a table. It's like the natural log of the absolute value of secant of x plus tangent of x plus c. So that one's kind of a table value. And you can get that from doing things like integration by parts, but if you just remember that and you have a single power, you're done. But if you have powers of like 3, 5, 7, and whatnot, what you have to do is you still use integration by parts, but you split off a 2. You split off a secant squared to use as your dv. That will antiderive to tangent of x. And then you use u as whatever's left over. Take the du, the power comes down, you subtract 1 from the power of secant, but then by the chain rule, the derivative of secant of x is secant times tangent. So you lose a power, but then you gain a secant back. So you really just get this in front. Secant stands alone, and you get an extra tangent of x, dx. And so then you end up with like this uv, which is fine, and then you end up with v du. And when v du happens, you now have a secant that turns out to be, decremented by 2. So it's still odd, but now you have this tangent squared. So now you have some extra piece that you can deal with, which we'll get to this piece here, or potentially this piece. Anyway, so that's kind of, honestly, it's kind of a nightmare scenario because it ends up being you have to do integration by parts to generate all the next things we're going to do. But hey, the next one is if m is even. So what that says is, okay, this is even. It doesn't matter if this is 0 or whatever. It's just if m is even. The reason why we can do that is that if it's just like secant squared of x, that antiderives directly to tangent of x. But if it's like secant to the 4th or secant to the 6th, and then there's tangents, we have to be a little more careful. So what you're going to do here is, since m is even, you can represent it as 2 times a number. So we have that secant to the 2 times a number x, tangent to something x. What we're going to do is we're going to split off a secant squared. We're going to split off a secant squared because the derivative of tangent is secant squared. So then, so instead of being 2k here, it's going to be secant squared x. And instead of being to the kth power, it's to the k minus 1th power because we split off 1 over here. So then the next thing we're going to do is we're going to take everything in this secant squared, every secant squared here, and we're going to convert it to 1 plus tangent squared x. So we're going to take everything here, and then we're going to convert it to 1 plus tangent squared x. And we're doing that because just like with sines and cosines, we want to have a bunch of things and then a dangling piece that gets sucked up in a u substitution. So we have all tangents and then a secant squared x dx. So once we've done that, we take a u substitution of tangent of x, and then its du is secant squared x dx. So again, that gets consumed by the u substitution, becomes du, and then you have 1 plus u squared to the k minus 1th power, u to the, whatever tangent was here, u to the n du. So you can just sort of throw it out there. So again, if m's even, that's kind of your ideal scenario. It tends to just kind of work itself out. It becomes a polynomial. Life is good. Now, if you have the case where m is specifically, m could be non-zero and it could be like even. If m is even, you really shouldn't use this, but you could. I don't know that I would recommend it. But if you have a case really where m is odd and n is also odd, this is kind of where you have to go. So if they're both odd, that's what you have to do. So then what we say is, okay, well then n is some sort of 2k plus 1, right? It's some even number plus another, because that's how odd numbers work. Our goal here is to split off a secant and a tangent. So again, if they're both odd, or one's non-zero, you at least have some secant and some tangent that you can just kind of split off to the side. So I'm going to take these two here, and I'm just going to say, all right, I'm going to represent it to look like this: secant to the m, tangent to the 2k plus 1. So then I'm going to split a secant off, so I have to subtract 1 here, and I'm going to split a tangent off, so I have to subtract 1 there. And then I'm just rewriting this as tangent squared of x to the k. So now I have a secant, some sort of tangent squared, and then I have a secant x tangent x dx at the end. From there, we're going to replace every tangent squared of x with its Pythagorean identity, secant squared x minus 1. So this stays the same, no change. But tangent squared x now gets replaced with secant squared x minus 1. And so again, we're doing this because we're trying to get this piece here to disappear with the u substitution. So now here we let u be equal to secant x. Its derivative is secant of x tangent of x dx. So then this becomes u to the m minus 1. This becomes u squared minus 1 to the k du. That's a polynomial. Polynomials, you can do the power rule. You're done. The final case, or not final, but the other case is a little trickier. In this case, you have only tangents. You have no secants. So the problem is that you need secants. You notice that we kind of use them. We either had like a secant squared x dx, or we had a secant x tangent x dx. Like, we need the secants to be there for our du step. So we're going to generate them. We say, well, I got tangents, maybe I can turn those into secants. And it turns out you can. Now, the only other... No, I'm sorry, this is fine. I was going to say something else. What we're going to do here, since we know that the tangent isn't even, we can represent it as 2k. So we have at least a 2. We might have 4. Sure, if it's 0, then that doesn't matter, because then m is 0 and n is 0, and your antiderivative is just x, because it's 1, right? Anyway, it doesn't matter. So what we're going to do is we have this, so I'm going to say, all right, instead of tangent to the 2k of x, or tangent x to the 2k, I'm going to rewrite that as tangent squared x to the k. So then I'm going to split off one tangent squared. I'm just going to take one of those tangent squareds and throw it out to the side. So now this is to the k minus 1, and I have an additional tangent squared x dx on the side. This tangent squared x, now I'm going to convert that into a secant squared x. I can use that Pythagorean identity to get a secant squared x minus 1. So it goes from here, this piece now becomes secant squared x minus 1. This is kind of ideal, because if u is tangent squared, or if u is tangent, then du would be that secant squared x. But the problem is I have secant squared x minus 1. So what ends up happening is I actually have to split this into 2 separate integrals. One where the secant squared x is kind of built in, and I can just do a u sub and I'm done. But this one is now another tangent squared x to the power. So this is really just this case. Now there's a minus here, but it's the same case, but instead of a power of the k, it's to the k minus 1. So the reason that's problematic is because if it was just tangent squared, you only have to do it once and you're done. But if it's tangent to the 4th, you have to do it. If it's tangent to the 6th, you have to do it. You have to keep going. And so what you might have to do is on this one, you might have to do it again. Like, this is solved. This one, you might have to do it again, and then you might have to do it again. So you have to repeat doing 4 or again 2, because this integral will use this methodology. And then the final one, which is sometimes the best place to start, even though it's the final one, is the idea of converting to sines and cosines. Now remember that secant is 1 over cosine, and tangent is sine over cosine, and sometimes turning them back into sines and cosines, you can get some interesting cancellations, and that's going to make your life a lot easier, because we might get the case where we can use a simple u sub and avoid any of this, or we might get the case where it's sine and cosine to a powers, and frankly, I like the rules for sine and cosine powers a lot better than I like the tangent secant ones.